So we would like to discuss what it means to have completeness, to discuss the notion of completeness in a norm space. And to do so, we should better begin with the real numbers. So in the real numbers, we have this very important property that any Cauchy sequence converges. Okay, so let's begin with what a Cauchy sequence is. So a Cauchy sequence is by definition a sequence that seeks to converge. And how do we know that? Or how is that defined? So let me just write this as a sequence that seeks to converge. So it's a sequence whose terms come very, very close to each other. So AN is called Cauchy from the name of the French mathematician who actually did so much significant work in founding modern analysis. So AN is called Cauchy if for any epsilon greater than 0, for any small number, there exists a knot such that if n comma m are greater than a knot, then an minus am is less than epsilon. Sometimes a simpler way to say this, but actually it requires exactly this further explanation, is that an is Cauchy if an minus am tends to 0 as n comma m tend to infinity. Like I said, this is this definition is a little more precise, and it's the one that we use for most practical purposes. Basically, what the statement says is that Cauchy sequences, meaning sequences that seek to converge, and convergent sequences, sequences that actually converge, are the same. And in order to understand the significance of this, it would be a good idea to understand that this statement would not hold over the rational numbers. So over the rational numbers, this statement would not be true. So for example, if we have the sequence of approximations of square root of 2, we can actually give one using the Newton-Raphson method, but let's say that you just take the decimal finite expansions of square root of 2. So you would have something like a1 being equal to 1.4, and a2 would be 1.41, and a3 would be 1.414, and so on. Then this sequence has terms that come very, very close to each other. As n tends to infinity, the difference between such terms is minuscule. However, if our universe consists of the rational numbers, if we have nothing else beyond the rational numbers, then this sequence will not find any place to converge, which means that it's as if we're detecting the existence of a hole where normally the limit of this sequence would be. So, in other words, Q is non-complete, whereas R is complete. Okay? So, if we have now a normed vector space, so let V equipped with a norm be a normed vector space, then we can define convergence of sequences and Cauchy sequences in exactly the same way as we do over the real numbers. So if AN is a sequence of elements of V, or, let me write it as UN. It doesn't really matter, but I feel better thinking of the of vectors as being described by the letter U. Then we say that UN converges to U if the limit of the numerical sequence of the norms of the differences UN minus U is 0. Okay? Then we say that UN converges to U. So just to give you a simple example, let's say we are in R2, and let's say that we have the one norm in R2. Take the sequence, so UN, let it be, let's take something fun, okay, so 1 plus 1 over n, and 1 plus 1 over n to the n. Okay, let's take this sequence, right? One can easily show by using the fact that the corresponding numerical sequences have limits, that this will converge to 1, comma, e. Okay? So now we can also define Cauchy sequences. So if UN is a sequence of elements of V, then UN is called Cauchy if for any epsilon greater than 0, so I'm going to completely mimic the first definition of Cauchy sequences that I gave you, which you can see it's in terms of the absolute value. And of course, anything you say about the absolute value can be rephrased in the context of vector spaces by replacing the absolute value with norm. If for any epsilon greater than 0, there exists a knot in n such that an minus am, actually, you see it, it's not an, it's un, right? So un minus norm is less than epsilon for n comma m greater than n naught. Okay, so in other words, this is a sequence of vectors that seeks to converge. It's a sequence for which the differences or the norms of the differences un minus um tend to 0. So V will be called complete if every Cauchy sequence of elements of V is convergent. Okay, so again, we have a context similar to the real numbers where convergent sequences and sequences that seek to converge are the same thing. So every sequence that seeks to converge finds a place to converge to. And that's exactly what a Banach space is. So a Banach space is a complete normed linear space. And of course, one would argue, why is completeness so essential? And understanding Banach spaces, part of understanding Banach spaces has to do with understanding why we couldn't do without completeness. And that will be one of the things that we will try to establish. And that's all. Thanks for watching.